Hello everyone, thanks for coming. Today we are going to do a review of our week 8 lecture. So in this week we introduce the Lagrange multiplier and then we do a brief introduction of double integrals for multivariate functions. So a function of multiple variables f of x, y, z given a constraint g, x, y, z equals to k, and then we wish to find the minimum and maximum of f on the surface g, x, y, z equals to k. The minimum and maximum of f are taken when the gradient of f equals to lambda times the gradient of g. Lambda is a scalar whenever the gradient of g does not equal to 0. Lambda is to be determined. That is to say, if the gradient of g is non-degenerating, then the gradient of f at the maximum and minimum of f on the surface g, x, yz equals to k must be at the same direction as the gradient of g. So that is for the situation where there is only one constraint. Given two constraints, g, x, y, z equals to k and h, x, y, z equals to k, c, then the maximum and minimum of f given those two constraints are taken when the gradient of f is a linear combination of the gradient of g and the gradient of h. Here we suppose that the gradient of g and the gradient of h are non-degenerate, which means that they are not 0 all the time. So that is to say, the gradient of f at the minimum and maximum given the two constraints must be a linear combination of the gradient of g and the gradient of h. Next, we introduce a definition of double integrals. First, we define the double integrals are rectangular. So we split the rectangular into many sub-rectangulars, the union of aij. Each aij is a small rectangular, and those aij's are the intersection of those aij's are the empty sets. The double integral is defined as the limit or the summation f xij star yij star times the area of each sub-rectangular delta aij. Delta aij here indicates the area of the sub-rectangular aij. Note that the double integral of continuous functions always exists on rectangles. So that is to say, this limit always exists for continuous functions. However, it is not realistic to evaluate the double integral of a function using the limit definition. Therefore, we define the iterated integrals, and then we introduce the relationship between the iterated integral and the double integral. So first, for a function f of x and y, we integrate over y for a fixed x. In this case, we get a function a of x, which is the integration of x, fxy, or over y from c to d, and then we can integrate a of x with respect to x from a to b to get this iterated integral. That is to say, we first integrate over y from c to d for f of x and y, and then for this a of x, we integrate over x. We have the Frobenius theorem. That is to say, if f is a continuous function on the rectangle, then the double integral, the value of the double integral equals to the value of the two iterated integrals. The first is we integrate over y and then integrate over x. The second is we first integrate over x and then integrate over y. There are several properties of double integrals. For a rectangle region, the double integral of the summation of two functions is the summation of two double integrals, the summation of the double integral of f and the double integral of t. Suppose c is a constant, then the double integral of the new function c times f equals to c times the double integral of f on the rectangular region R. Note that for these properties, we can replace R with some general region D that is enclosed in a rectangle. Finally, if we have two functions f and t, and if f is always greater than or equal to t on this rectangular region R, then the double integral of f on R is always greater than or equal to the double integral of t on R. Thanks for listening.